Hello everyone, today I'll guide you through a hypothesis test which I conducted to analyze my data. The claim is from this article that data of 11,000 users on average spend 3 hours and 50 minutes on their phone, which makes that 3.25 hours. And starting with possible outcomes, our null hypothesis is new data shows that average people spend 3.25 hours a day using their phones, making that 3.25 our null hypothesis mean value. And below we have the alternate hypothesis which will point to a different outcome. In this case, the alternate outcome is that the mean value will be greater than 3.25, making it a one-tilt test. The reason why I made it a right-tilt test is that many people do work from home or require a screen to study, so I was honestly convinced that the average daily time would be higher. And to test this, I collected data from 33 different people because a sample size that is 30 or larger typically is sufficient to produce accurate results. The purpose is to determine whether the average value in my dataset is higher than the claimed value of 3.25 hours. Thus, a hypothesis test needs to be conducted to spot differences. Now, let's quickly skim through the population data we have at hand. The only information we have from the article is that the mean is 3.25 hours, alongside its sample size which is 11,000. Leaving the standard deviation as known as the variations of responses unknown. This is important, so please do keep this in mind. Moving on to my sample data, my sample size is 33 as I've collected results from 33 different respondents. This is my sample mean as known as average, which is about 4.303. The difference between the sample mean and the population mean is that it is only a small subset of the entire population. I use the Excel formula of the average bracket B2 to B34 because that is the column where I store my responses. The standard deviation is about 1.879. I use the Excel formula STF.S from B2 to B34. Notice how I put .S at the end instead of .P because .S formulas is meant to be used on samples while .P is for the entire population. So standard deviation represents the spread of the data collected. The significance level is represented by the sign alpha and it means the predetermined standard for deciding how much evidence is to reject the null hypothesis. 0.05% is 5%, which tells us that there is a 5% risk of incorrectly in rejecting the null hypothesis. 5% is chosen because it isn't too lenient nor too strict if the results are statistically significant. As mentioned before, the population standard deviation is unknown. Thus, we should conduct a t-test instead of the z-test because the z-test requires population standard deviation while the t-test does not. Choosing the correct test to carry out will lead to better accuracy in the statistics. I use Excel to apply the t-test formula to the experiment. For the t-test formula, it's a sample mean minus population mean divided by sample standard deviation over square root sample size. My test statistics is about 3.220. Next, we have the p-value, which is something that can determine whether we can reject our null hypothesis or not. The p-value formula in Excel for a one-tailed test is pt.dis.rt open bracket sample size minus 1 close bracket. If our experiment p-value is lower than the significance value, we can reject the null hypothesis, otherwise we cannot. So my p-value is 0.00147, which is significantly smaller than 0.05, so I successfully reject the null hypothesis. Margin of error tells you how much your result might vary if you repeated your study or survey within a new sample. So my margin error is about 0.666. So the Excel formula I used for the margin of error is confidence.t0.z because we are currently conducting a t-test. Open bracket alpha, comma, sample standard deviation, comma, sample size, close bracket. Upper confidence interval is the sample mean plus the margin of error, and the lower confidence interval is the sample mean minus margin of error. So this will conclude the range, or rather the sample confidence interval. This interval gives you a range of numbers that likely includes the true average for the whole population. And my final observation is that the population standard deviation is unknown. That's why z-test cannot be conducted, and that's why I follow up with the t-test, which uses on the t-test formulas. And my p-value turns out to be smaller than the alpha, which means that I can reject my null hypothesis because burst screen time in a day is proven to be more than 3.25 hours. In plain terms, my data shows that the true average is most likely above the claimed value of 3.25 hours. Thank you for watching.